Hi everyone. Just responding to your feedback from today's lecture. How does this expression convert to this expression? So for the people who are perhaps either unfamiliar with proportionalities or didn't have me last semester, I have a tendency to start with proportionalities and then transition into equalities. But basically all a proportionality symbol tells you is if I increase one variable, how does the other one change? In this case, the proportionality symbol tells us that as you increase the pressure, the concentration, the solubility increases. And we don't know exactly how it varies, but we know that it varies linearly. There's probably some single number here that will convert this from something in units of pressure to units of concentration. And generally, if I were to make a plot of pressure versus concentration, I know that that plot would have that relationship would look generally like this. So if I increase the pressure, the concentration goes up, and then the slope of this line tells you just how much the concentration increases as you increase the pressure, and that slope is equal to the Henry's law constant. So Henry's law, as far as I'm concerned, the most important thing to take away from Henry's law is just that as you increase the pressure above a solution, the concentration, the solubility of that gas in the solution increases. That's the general behavior that I want people to know. Henry's law is that it's explicitly linear. Your textbook will pointed this out, and I recognize I didn't quite emphasize this, is that not every gas follows Henry's law exactly. There can be deviations from Henry's law. Some gases don't quite follow a perfectly linear trend. They might have some curvature to them. They might go like that. But most of them still generally, their concentration increases with pressure. And that's mostly what this is saying, more or less. So what's the significance of this constant? Well, a couple questions about the Henry's law constant. Is it actually constant? Short answer, no. It changes, well, it changes with temperature because we know the solubility of a gas in a liquid changes with temperature. So this might be the solubility constant at one temperature. So I'll call this T hot. So this might be what the slope would look like for a single gas at one temperature. If I look at the solubility of that gas at a lower temperature, it's naturally at a single temperature, its solubility should be lower. We've already discussed how solubility decreases with temperature, so the actual value should be less, and the equilibrium, Henry's law constant, should be smaller as well. How does the Henry's law constant show how favorable an equilibrium system is? It gives you a measure of how naturally the gas likes to dissolve into a solution. So I'll give you an example. For instance, oxygen naturally does not dissolve in water as easily as carbon dioxide does, nor, I think, a little bit better than nitrogen, but those are both they have relatively low solubilities in water, so they have relatively low Henry's law constants. So they would both follow Henry's law, but this might be the slope for oxygen. This might be the slope or the solubility of something like carbon dioxide. So yeah, the point being that different substances, well, they just like we saw that different salts have slightly different solubilities with respect to temperature. Different gases have different solubilities with respect to pressure. They all generally increase, but they don't increase at the same rate. The rate at which they increase is related to Henry's law constant. And that's also dependent upon the identity of the gas. Are solutions always trying to increase disorder and decrease energy? How is entropy a driving factor? Yeah. So here's what I will say. The guiding principle for what a system will do, or what any reaction wants to do, or any process that occurs, is one in which entropy increases. Specifically, the entropy of the entire universe increases for every single process, meaning things all over the entire universe are constantly becoming more disordered. Now, I should qualify that because you can immediately think of cases where things things do become more ordered in some way. So an example I was discussing with somebody yesterday is Jenga blocks. You can certainly take a bunch of disorganized Jenga blocks and fit them all together, and that is a case where you are making something more ordered. That would seem to violate the second law of thermodynamics, that those Jenga blocks don't just spontaneously come together into a nice ordered tower. But the second law of thermodynamics doesn't just refer to a single part of a system. It refers to the entire universe. The entire universe is becoming more disordered. So individual parts of the universe can become more ordered, but at the expense that other parts of the universe become more disordered. So I exert energy, I burn sugar and expel it as carbon dioxide. I turn sugars, which are either solids or liquids, and I convert them into CO2, which is gas. So gas being the more disordered form. So even though I might be able to order a set of Jenga blocks, I do it at the expense that I'm making my carbon source, my carbon and my energy more disordered. So generally speaking, we will eventually get to this, that you can look at a single system and decide whether or not a particular chemical reaction is favorable, and it's generally most favorable when its energy is lowered and its entropy increases. But you can have systems where the entropy decreases and the process can still occur if its energy decreases as well. So yeah, how is entropy a driving factor? Okay, I'll give kind of a highfalutin statement to this. The natural process of everything is to become more chaotic, more disordered. And my personal interpretation for why that is the case, why the second law of thermodynamics is true, is a step back towards quantum mechanics. And one of the key principles of quantum mechanics is that everything is inherently random. So the motion of electrons is inherently random. The motion of protons is inherently random, meaning the motions of atoms are essentially, in their very essence, random. So the things that will occur are those things which are statistically most likely. Things which, okay, everything's random, but some things are more likely than others. And it turns out the most random, or rather the most probable configuration for most things, most systems, is ones where that system is very disorganized. That happens to be the most probable or the most likely outcome. So the universe is inherently random, so it will always choose the most probable outcome is the outcome that will occur most frequently, and that happens to be a disordered or a chaotic outcome. What's the difference between enthalpy and entropy? All right, that's a tough question, or it's an insightful question. They get confused a lot because they do sound a little bit similar, enthalpy, entropy, but they are drastically different. Enthalpy is a measure of energy. It's not technically internal energy, it's not just technically energy, it's a little bit of a technical difference, but basically it is energy. That's what enthalpy is. Entropy is a measure of how energy is distributed. Uh, you may have a substance, and that substance all has many particles in it, and those particles have energy. And the question is, how is that energy distributed among all of them? Do they all have equal amounts? Do some of them have a little bit more than others? That distribution, how things are distributed, it can be represented by the entropy of that system. But generally speaking, it's a measure of how distributed or chaotic or disordered things are. So enthalpy is more just a single quantity, energy. Entropy has a little bit more related to distributions of energy and how things are arranged, not just single quantity. How much is the total energy, but how is it spread out and dispersed? How is the carbon dioxide system supersaturated and then at equilibrium? So actually, it was both. I made a bottle of soda water. I charged it with CO2. And when I finished charging it, it was at equilibrium. So I had a certain pressure of CO2 and a certain concentration of CO2, and they were at equilibrium. Those are two arrows showing, okay, there's gas going into the liquid and there's gas going out of the liquid, or rather there's CO2 going into the liquid and there's CO2 going out of the liquid. But overall, I didn't see any bubbles forming. I didn't see any extra CO2 going in or any extra CO2 going out. At that point, the system was at equilibrium and it wasn't changing anymore. And the concentration in the solution was that given by Henry's law. So the solubility was somewhat determined by the pressure. It was at that solubility limit for the pressure that we had. So it was initially, when I first made it and I hadn't opened it, it was initially saturated. Because I've already pumped in as much CO2 as I possibly could into the system for a given pressure of CO2. As soon as I open it, all of a sudden that pressure drops precipitously, which means that the solubility, the preferred solubility of the CO2 in the water suddenly drops. Now the actual concentration in the CO2 is above that. It started at a saturated solution, it started at a high concentration, and then all of a sudden I get rid of that excess pressure, which means that the fundamental solubility should be significantly lower. It should be the solubility that corresponds to the ambient CO2 partial pressure at any given time, which is relatively low. So as soon as I open it, it then becomes supersaturated. It should degas saturated. And we saw that bubbles started coming out because as soon as we relieve the pressure, the solubility limit immediately changes. The preferred concentration immediately changes. It starts out above that, it degasses, and it drops back down to the solubility limit. So at some point, the soda goes flat. And once you do that, it then reaches the solubility limit. It reaches the solubility limit, and that's when it's at equilibrium again. And that solubility limit is then, we'll say that it is then saturated. So it starts at a high pressure. Then we go to a low pressure. But as soon as we lower the pressure, it takes a while for all the gas to come out. So before all the gas comes out, it's supersaturated. Once all the gas, once the excess CO2 comes out, it then becomes saturated. Okay, why do some solids' solubility increase with temperature while others decrease? that ends up being a more challenging question than I'd like. The so So I looked this up and I found a couple of explanations, some which I liked, some of which I didn't like. One that I saw that I didn't like, but I guess I will mention it because it may come up at some point. It will come up at some point, but let me deal with it. Is that, oh, those solutions are exothermic. And we'll later discuss something called Le Chatelier's principle, which is a general way to think about how an equilibrium system reacts to changes. So according to Le Chatelier's principle, exothermic reactions become less favorable at high temperatures. So if something like sodium sulfate or cerium sulfate, they happen to be exothermic, meaning that as you go from solid to aqueous, that's a release of energy, and exothermic reactions generally are less favorable at high temperatures. I didn't quite like that explanation because lithium chloride we saw on last Wednesday, that one is an exothermic reaction. And lithium chloride's solubility does increase with temperature. So I don't actually like that argument. My current argument, my personal interpretation is that there's likely entropic effects that are not they are not obvious, that in some way the sulfate is interacting with water molecules and causing them to become more ordered and more clustered around sulfate. So there's unexpected cases where normally you expect if a solid dissolves in solution, that's an increase in disorder, but the presence of that solute can affect the local structure of water molecules and cause them to become more ordered. So, point being that it's not a simple explanation, and I was looking this up. Even within the last 20 years, people don't seem to have come to a simple explanation or a definitive explanation for why some salts seem to buck the general trend. So I recognize that's a bit of a I find that an unsatisfactory answer, but that's what research frequently is. How does, let's see here. How does pressure affect the solubility of solid solutes? So we spoke at length about Henry's law, how gases' solubility increases with pressure. I didn't say much about solids. That's because generally the solubility of a solid is independent of the external pressure. I should probably clarify that Henry's law is specifically referring not just to the external pressure, but it's the external pressure of the gas. So if I was dealing with something like CO2's solubility, its solubility is dependent upon the external CO2 partial pressure. So it's dependent upon, to some extent, it's dependent upon the concentration of the gas, of the solute outside of the solution. I say concentration because you can make an argument from the noble ideal gas law. The pressure of a gas is equal to N over V times RT, and this moles per volume, that's molarity. So at a constant temperature, you can think of pressure as being like a concentration. But solids, for the most part, don't have a concentration, or they do, but their concentration is invariant. So to some extent, I will say that solid solutes are their solubility is independent of external pressure, and yeah, that's what I'll say. I had one request for more examples, which we might see on a quiz or a test. Yeah, I know those are good. I will try my best to incorporate more of them. Why doesn't collision theory apply to gas solubility at higher temperatures? Or why can't you use collision theory to explain the solubility? Actually, you can. That's an alternate interpretation, and one which I recognize perhaps I should have offered as an alternative explanation. Collision theory, one of the basic tenets of collision theory is that as you raise the temperature, particles start moving more quickly. So if I had a solid where all the particles were tightly bound together. If I have a solid. If I heat them up, they are more likely to go into solution. So I'm imagining that this is a liquid here. I heat them up, they start moving more quickly. They're more likely to break away from each other just because they're moving more rapidly. They're more likely to break away from each other and dissolve into solution. So that's one way you can explain why solubility increases with temperature. Conversely, if you have gas solutes that are typically gases, and they're already in, so this is supposed to be a gaseous phase, this is supposed to be a liquid phase, and over here that's supposed to be a solid phase. So if I have gaseous solutes and I raise their temperature, yeah, they start moving more quickly, and so they're more likely to break away from the liquid and go into the gaseous state. That's the kinetic theory of gases. That's another way to interpret why the solubility of gases decreases as you raise their temperature. Why is sodium bromide the most challenging to make a supersaturated solution? In that particular context, the reason why it was the most difficult was because, I'm going to change this here, change my chart a little bit. It was the most difficult to make a supersaturated solution because you have to make a supersaturated solution, you have to change the temperature of the solution, or rather change the solubility of the solution. So so this might be the solubility of sodium bromide. This might be the solubility of something like potassium nitrate. So if I want to make a supersaturated solution at a particular temperature, I need to change the temperature to a point where it's more soluble, make the solution at that high solubility point, and then cool the temperature back down to a regular point, and then its concentration is actually well above its preferred concentration, and then it's supersaturated. For something like sodium bromide, the slope of its curve was so flat that it's nearly invariant with temperature. So I can heat it up as much as I like, or rather I can heat up the solution as much as I like. I'm not going to be able to fit an appreciably higher concentration of sodium bromide is. Now, if your fundamental question is why is sodium bromide have such low solubility, I admit I don't have an immediate answer for that. I'll look into that. But yeah, frequently it can be difficult to explain the fundamental solubilities of certain substances. Usually it's related to the degree of intermolecular forces. So I'll make an argument, the bromide ion is relatively large, even though it has a negative charge and water might want to attach to it. Because it's really large, water molecules can't really get close to it. So the favorable interactions with water and bromide are relatively negligible. So generally, if you want to make a solution, you need to overcome the solute's intermolecular forces and the solvent's intermolecular forces. Those both require an increase in energy. And when you bring them together, that's when the energy drops. And that's the favorable interaction part. Bromine's a relatively large molecule, so the oxygens can't get close, so they don't have as much opportunity to have very favorable interactions. So that's my hand-wavy explanation for why sodium bromide has a relatively low solubility. If carbon dioxide is less soluble at high temperatures, then why does CO2 dissolve more in the oceans and cause ocean acidification? So that's a good question. It's because there's not just a single factor for why that determines the solubility of a gas in a liquid. Yes, one factor is temperature. The solubility of the CO2 should decrease with temperature, and it does. It does decrease with temperature. And so, to a first order approximation, we might assume that as we heat up the oceans, CO2 should leave the water. Fair enough. But that's not the only effect that's going on with global warming and climate change. The underlying reason, or one of the underlying reasons why we're experiencing global warming, is because we are increasing CO2 content in the atmosphere, which means we're increasing the partial pressure of CO2 in the atmosphere. That's the root cause for global warming. So because you have higher external pressures of CO2, that leads to, if you increase the partial pressure, you increase the solubility, you increase the concentration. So there's two effects, and it turns out the higher partial pressure of CO2 is more important than raising the temperature of the ocean, of the world's oceans. Yeah. Somebody made a correction here. To me. Ocean acidification doesn't cause coral reef bleaching, rising temperatures do. And you're right about that. I've looked into this. I admit I'm not a biologist, let alone a marine biologist, so I made a quick assumption, which turns out was incorrect. So I looked into this. The bleaching occurs when algae in coral leaves the coral. The coral normally is stressed in some way, and it expels the algae. The algae are what give the coral their bright color. And so anything that would stress the coral in some way will result in bleaching. And the dominant effect is actually rising ocean temperatures. That's distressing the coral. There are other factors, and I guess I feel a little vindicated because I looked into this. Ocean acidification is one of the factors that can cause coral to be stressed and expel algae and become bleached, but you are correct that the dominant effect, the major cause, is rising ocean temperatures. On the tests, are solution calculations going to be tested in terms of stoichiometry? Probably not. I don't think that's a terribly... I will not have stoichiometry questions. It's just a straight stoichiometry question where I give you the molarity and the volume, and I ask how many are asked. Given this particular concentration of volume of one reactant, how much solute or how much product can you make? I'm not going to ask questions like that. Y'all have already been tested on that. Now, reaction stoichiometry might come into play in the sense that you need to look at molar coefficients in the balanced chemical equation. That might come into play, but not so much, looking at limiting reactants or looking at stoichiometric ratios. Mostly looking possibly at, you may have to consider stoichiometric ratios, but that's not my primary concern at this point. So I don't anticipate putting many questions of that kind. They may be tangentially related to stoichiometry, but not your standard stoichiometry calculations. Okay, so the last couple questions here. Is the Henry's law constant always moles per liter atmosphere? No, it doesn't have to always be moles per liter atmosphere. It frequently will be. All the Henry's law constant does is provide some way of connecting something that's a pressure to something that's a concentration. So you have seen that there are multiple ways to express pressure units, whether there's multiple units for pressure. There's atmospheres, pascals, millimeters of mercury, torr, so on and so forth. And there's multiple units for concentration. And all I will say about the Henry's law constant is that its units needs to be consistent with the units of the other species. I'm not planning on doing anything that's drastically... I mean, concentration I'll almost always give it in units of molarity. Pressures will frequently be in units of atmospheres. I may do it pressures in units of kilopascals if for some reason I decide to make the problem just a little bit more challenging by throwing in some extra unit conversions and dimensional analysis. But I don't plan on doing that. Last question. Is carbonated water, which is acidic, bad for us? Not really. There may be a small amount of damage that it does to your teeth, but keep in mind your stomach acid. So you guys saw today the pH of carbonated water isn't that high. It's around 4-ish, maybe a little bit lower. Your stomach acid is all the way down with a pH of 1 to 3.5. So your stomach acid is actually inherently more acidic than the carbonated water that you drink. So that's just like in terms of the liquids going into you. You don't have much to worry about there. Your body also has what we call a buffer system, which maintains a relatively constant pH. We'll talk about buffer systems in several weeks. But no, you don't have to worry about drinking soda anytime soon. All right, that's all of your feedback for today. I will see everybody on Friday.